Hello, today we're going to be talking about surface tension and aqueous solutions. We're going to find out how um, a water strider, such as this picture here, is able to just walk on top of water or stand on top of water, even though it's more dense than water, or how we can float a paper clip in water. We're going to find out how the Great Pyramid of Giza is able to withstand 5,000 years of rain and all kinds of forces and still be there. And so let's dive right in with surface tension here right off the bat. And we're going to talk about our first definition for today, and that is the definition of what we call surface tension. And this is going to be the phenomenon in which the surface of a liquid is going to act like a thin elastic sheet. And we saw this in class yesterday, that thin elastic sheet. And this is where the liquid is in contact with gas. Now, we're just going to give some examples of surface tension first off, and then we're going to talk about the why of the surface tension. But there's the definition. So there's a water strider there. You can see kind of the indentations here every time its appendages are touching the water. He's just sort of kind of be able to walk across the top of the water. There's of course, a drop of water on a leaf. And again, the reason this all comes about is due to the hydrogen bonding. And we talked about this a little bit in last night's video, but in hydrogen bonding, we're going to have hydrogen bonded directly to a very electronegative atom such as oxygen. It can also be nitrogen and fluorine. And because oxygen is so electronegative, attracts those electrons to it, all those electrons, we get this force of attraction from one oxygen molecule to another water molecule, especially the hydrogen portion of that water molecule, just like that. And then that molecule will be attracted to another water molecule, and so on and so forth. And so you have sort of the skin forming, this force of attraction of water molecules being attracted to each other. It's really what this is all about. And I want to show you a quick little video on a slow motion video on this same principle. This video is off of YouTube, and these are the slow-mo guys. And they're shooting just drops of water at 2,500 frames per second. Think of taking a picture, 1 picture per second would be 1 picture or 1 frame per second. 2,500, very, very slow. And so we can see that the water is just, while we can't see the molecules, we can see that attraction that water has to itself. The water molecule almost just bouncing off of the other water. It's being dropped on before it just sort of sinks in there. So there's really that force of attraction. Is why water or why water forms a round droplet is because of the force of attraction, that surface tension that occurs. Okay, so let's dive in and talk about one way we can decrease surface tension, and that's the idea of using a surfactant. And a surfactant is going to be anything that decreases surface tension of water. A couple real good examples of surfactants, and I showed you this yesterday in class, was if we put a little bit of soap or a little bit of detergent in water, it's going to decrease that surface tension, that force of attraction between those water molecules, and it won't allow surface tension to occur as easy. Okay, one of the next ideas that I want to talk about is the idea of hydrogen bonding and how it relates to vapor pressure. And so let's take a look at that real quickly. We did define vapor pressure before, and that's going to be vapor pressure is the gas pressure above a liquid due to evaporation of molecules. So if we were to draw, sorry about that, that was the bell, the 10-minute bell. If we were to draw a container, and this is a container, not a very good one, but that's okay. And this container's got some liquid in it. Let's say we've got some water in the liquid form. What's going to happen is that water is going to evaporate over time. Now, the molecules that are going to be up here are going to be bouncing around, and they're going to create pressure. They're going to create a gas pressure, and that gas pressure is called vapor pressure. It's the gas pressure above a liquid due to evaporation of molecules. Now, hydrogen bonding is going to give water a relatively low vapor pressure. Do you know why? Well, hopefully you can think that there is hydrogen bonding, which is this force of attraction from one water molecule to another water molecule. And that's kind of holding water in the liquid state. It doesn't want to evaporate as fast as maybe some type of compound that does not have hydrogen bonding. It would have more vapor pressure. It would be easier to evaporate. Okay, let's talk about solutions now. We're going to talk first off about an aqueous solution, and this is going to be a substance that dissolves in water. Now, we have two parts to an aqueous solution, two parts of it. The first part is going to be called the solute. This is going to be the substance that gets dissolved in an aqueous solution. This is going to be present in the smaller amount. We also have the solvent, which is the substance that is dissolving in the larger amount, and this is usually water. And so if we take these two together, we add a solvent, which is the water, and the solute, which is the dissolving substance, we get a solution overall. And this is an important idea governing a lot of chemistry, because a lot of chemistry occurs with solutions. And so what will water dissolve in? Or I should say, we should probably change that and say what will dissolve in water. How about we change that sentence around there? What will dissolve in water? And many ionic compounds will dissolve in water. We'll talk about that in a minute, who does and who doesn't, as well as many polar molecular compounds. And we'll talk about that too in a second here. Okay, so let's talk about the solution process next. Now, there's a lot of definitions in this unit that we're working on. Solvation is the definition that we're going to be talking about, is the process that occurs when a solute dissolves. And let's give the example of sodium chloride. And I'm going to draw sodium chloride solid before it dissolves. And remember that sodium is going to form positively charged ions, and chlorine is going to form negatively charged ions. We have a metal and a nonmetal, so we definitely have an ionic compound. And so we would have positive sodiums bonded ionically to negative chlorines, which would then be bonded to positive sodiums, negative chlorines, positive sodiums. And this just keeps going this way when we have a solid ionic compound. We have this crystal lattice structure, just like this, repeating positive and negatives. And of course, it would be in 3-dimension, which I did not draw. Now, if we place this in water, as we know, when you place salt, sodium chloride, in water, it dissolves. And that's the ocean is very salty with salt dissolved in it. Or if we put a little bit of salt in some water, maybe we're using to cook with, we know it dissolves. So what's going to happen is the water molecules, which of course are oxygen bonded to hydrogen, as we now know, these guys are going to have a slight, sorry about that, yet another bell. They have a slight negative charge. So this slight negative charge is going to be attracted to the positive charge on the sodium. And then we'll have another water molecule come in here, and we'll say the hydrogen here is going to be attracted to the negative ion. And so what's going to happen is these ions are going to come off. And so let's say if we have a negatively charged chloride ion, it's going to be surrounded by the hydrogen portion of a water molecule. And we're actually going to have it surrounded. A bunch of water molecules are going to surround this guy, just like this. And they're not bonding with it. It's just this force of attraction. And when this occurs, we call that, like we said, we call it solvation. Now, a couple things that we do need to know about as well, a couple more definitions for us, and that's the definition of soluble. Now, if we have the force of attraction between the water and the ion, if that force of attraction is greater than the force of attraction between the ion and the ion, the sodium and the chloride, we say the substance is soluble. Or an easy way to say it is it's going to dissolve in water. So anything that's soluble dissolves in water. Solubility would dissolve in water. Now, if you're insoluble, another definition, the force of attraction between the water and the ion is less than the force of attraction between the ion and the ion. So the ions have this really great force of attraction that holds them together, and even when you put them in water, they don't want to dissolve. And calcium carbonate is a great example of this idea, which is also called limestone. And here is the Great Pyramid of Giza, and this thing has been around for somewhat close to 5,000 years. And even though in the desert they don't get much rain, it does rain occasionally, and there is moisture in the air. But the pyramid is still there because the covering of it is limestone, which is very insoluble in water. And because the calcium and the carbonate ions are just attracted to each other so tightly. And that is today's talk on soluble and insoluble compounds, solutions, as well a little bit on surface tensions. And we'll talk tomorrow.